So welcome everybody. I can see Giovanna, Nina, Willa, Kian, a lot of people coming in. People are saying I look younger with this, my mustache gone. I'm a little sad about that, but it got washed down the sink. So good morning to all. I can see 250 of you here. Let me share my screen to kind of get things started. I'm working from home today. So you can see I'm in my, my son's bedroom. Today we're starting in on chapter 11, actually, which is on waves. This is the last chapter we'll be doing in this course. And so today I'm going to talk about the difference between transverse and longitudinal waves. I'm going to talk about sinusoidal waves, and you'll see a lot of equations that are actually similar to the equations that you saw back in chapter 10. Okay, because this is any little part of a wave is oscillating with simple harmonic motion. And we're going to talk about wave speed and how that's determined. Let me just make sure my chat is showing here. I also very much hope that I don't have an internet issue today, because this is I'm actually on a wireless right now. The midterm last night, why don't we start by talking about that? I'm not going to go through the solutions because I did post them, but it was a very difficult midterm. And some might call it a bit of a bloodbath. So the average was 49%. So it was a difficult test. And what you're seeing in this histogram is actually the number of questions out of 10 that you got correct. Does that make sense? So you've got, if you got one question right, you're there. There was about 20 of you in that situation. If you got 2 questions correct, then there was about 50 of you in that situation, etc. Most of you either got 4 or 5 questions correct. 5 of you got all 10 of them correct. And so what I did is I adjusted the scores using a breakpoint system. So this is a mapping where you map 0 is 0 and 100 is 100. So those people don't get their marks changed. Everyone else gets their mark boosted up on this midterm, as you can see. So 40 maps to 70. So if you got 4 questions correct, that's a 70, and you got a B on this test, because at UT, B's start at 70, etc. So the adjusted mark, I did try posting it. It takes a little while for it to update on Quarkus, so it should show up in the next half hour or so. So what you'll see on Quarkus under the gradebook, I'm looking at the chat window here. Actually, I'm going to turn off the attendees. So you'll see your raw mark, and that will be that'll link to the speed grader, I guess. And then I've posted a new item called midterm 5 adjusted mark. That'll be your actual mark. That's come from this mapping here. And I haven't looked specifically at the questions. Oh, correct answers are hidden. Yeah, that's another adjustment I have to do on the Quarkus settings. So you might not be able to see which questions you got wrong, but I will go and fix that after class today. So I've posted detailed solutions. Let's look at the next slide here. Solutions video. It took 21 minutes to go through very carefully and read out the questions and write out my solutions. They are here. So there's a PDF showing where I've written out, and there's a whole video on YouTube that you can click on, which should be live now. And I did it for both the alternate sitting and for the regular sitting. This is kind of it. I mean, it is possible. Someone just asked me fast, what if the two lowest test scores are the same? Then I'm only going to drop one of them, right? Basically, I'm going to take the top 4 midterm scores out of 5, and that will form your midterm mark. And Annie, I haven't done the analysis, so just finished marking it this morning. So this is kind of all I know. I do want to get on to waves though, if you guys are okay with it. I mean, the final exam is covering a lot of material, right? And the question is the final as tough as this test? And I think that a lot of you have studied a lot of this stuff from the first half of the book, chapters 1 through sort of 6 or something in high school. And so it's familiar ground, whereas the chapters 7 through 11 are kind of different. And especially torque, I think chapter 9 is a particularly difficult chapter. And the final will be 2 parts. There'll be a 10 multiple choice to do in half an hour, followed by 2 written questions to be done in 35 minutes. It's all on December 17th. Emma, did you want to unmute?
Yeah, hello. I just had a question about the LASSO survey you were talking about on Monday. I didn't receive an email from that, so I was wondering if all the emails have been sent out.
You did not receive an email?
No.
I'm having a little trouble hearing you. So yeah, if you did not, I'm turning up my volume here. If you did not receive an email from the LASSO, that's not good. Maybe pop me an email or something and see, I can go on there and try to resend it to you, or it may have something to do with just the email that's listed in that I got from at the beginning of the semester. Yeah, it's worth an extra 2 homework points if you do those surveys. So just pop me an email with the Physics 131 fall. Okay.
Thank you.
Okay. Finals not get dropped. LASSO surveys are due, I think, on December 10th, last day of classes. Okay, everybody, let us continue on chapter 11. I have posted homework 11. You can take a look at that. Most homeworks were due on Mondays. Homework 11 is due Wednesday, December 9th. It's the last one, so there's just 2 days more for you to work on it. Also, I have posted one of these not for homework credit items called videos and practice for chapter 11, which I would recommend that you should go check out. It's got this cool video of it's actually a ripple tank. So it's a little tank of water that they've put on an overhead projector, and they're making waves in it. And when the light shines through, you can see those waves as shadows in the overhead projection. And so they're showing plane waves that are going through a little opening in a barrier and then coming out as circular waves. And there's another one of these Khan Academy style videos about mechanical waves, which I think is pretty useful. Tells you where all this distance and lambda, which is the wavelength. We're going to be talking about that today. It looks like a fridge. Someone said that looks like a fridge. I guess it does. It doesn't look like that in the video. Okay, last day I asked 2 of the 5 senses depend on waves in order to work. Which 2? Well, it's hearing and sight. So in this course, chapter 11, we're going to be talking about sound, which is a wave, and we're talking about the decibel system and things like that. In Physics 132, Professor Seelfen is going to be spending a couple of chapters dealing with optics and the physics of light. So sound is a pressure wave which travels through the air. Light turns out to be a wave in the electric and magnetic field. So part of what you're studying in Physics 132, which starts in January, is electricity and magnetism and how those relate. And so it turns out that when you look at Maxwell's equations for electric field and magnetic field, there's a wave phenomena in the electric and magnetic field, and that's what light actually is. Notes here. Okay. So chapter 11. This is about mechanical waves, not just sound, but any mechanical waves. And we're going to start with talking about waves on a string, actually. So we talked about in chapter 10, a vibration is a periodic linear motion of a particle that's going back and forth about an equilibrium position. When many particles vibrate and they're right next to each other, then their energy of vibration can be carried a long distance through space, basically by these particles bumping against their neighbors. That's how it works. Examples being water waves. That's what we're kind of showing here is a simulation of water waves. What you can see it's going on is that every individual particle is actually tracing a little circular path. Okay, but then what you see on the surface, you see these waves that are going along. And so there's two kind of things going on. One is there's the wave, which is carrying energy, which is moving along here from left to right. And the other is the vibration of the particles within the wave. And that can be in different directions. In the case of a water wave, it's going around a circle. Light turns out to be a transverse wave in electric and magnetic fields. Sound is a longitudinal wave. You see the air particles vibrating back and forth and bumping into their neighbors. Look at what's going on in the Q&A here. Anonymous attendee asked when I'm going to remark those midterm fours. I haven't done that yet. Probably maybe today or tomorrow. And the final two written questions are going to be basically from a particular chapter, but they might involve previous chapters as well. And I'm not going to tell you which chapters. And yeah, the energy that's traveling along is the mechanical energy. I guess it's a combination of the potential and kinetic energy. The potential energy from the springs, and then like if these are hooked together by springs, and the kinetic energy of actually motion. Let's go back to this. Here's an example of how waves spread out in space. So if you imagine a cat licking the water, then what that is it's a vibration or a disturbance at a particular point in space. That is called the source. And then this sends ripples, which are the waves themselves, out in sort of this circular wave fronts, which spread out. You can sort of see those there. So away from the tongue. Tongue is the source in this case, across the bowl. And the medium here is the water. So those are sort of three vocab words: source, the waves, and the medium. And we can look at these sort of overhead pictures of a beach ball falling down into water. So what you have is the source here in the middle. Then you have what are called wave fronts. The wave front is sort of the locus of all the points connecting the crest of a wave. So this is a wave front as viewed from the side. As viewed from the top, it makes this circle. And these concentric circles move away. They all move out and their radius gets steadily bigger and bigger. Oops, didn't draw that very well, as the thing spreads out. So these are called two-dimensional waves. Circular waves. So if you have a point source and it spreads out in 2 dimensions, you get these circular wave fronts, which go away from the source. Yeah, the wave front is a crest of a wave. So sometimes there'll be troughs like that. Each wave front marks a crest. Question from Annie there. Okay, so that's in 2D. We should also remember, especially when we get more into sound, that you can have 3-dimensional waves. And this is sort of the analogy. What happens in 3 dimensions is that if you have a point source, like maybe a speaker sort of out in the middle of space, if it is radiating sound in all directions, then the wave fronts will be spheres, each of them centered on the source. So they're called concentric spheres because they all have the same center, which is the source. And though the radii of those spheres is all increasing at the speed of sound in this case. And this is also how light can travel out. So if you have a candle or something, which is a point source, and you go far away from it, then those light waves spread out. And we deal with this in astronomy a lot because stars are very, very far away. We treat them as point sources. So when those spherical wave fronts hit the Earth from a distant star, they come in as plane waves, so just big planes. Okay. I want to talk about transverse versus longitudinal waves. So what this is about is, so this slide's on transverse and the next slide's on longitudinal waves. Okay, transverse. So what this is about is the direction of the vibration of the particles versus the direction that the wave itself travels. So a transverse wave is when the medium vibrates perpendicularly to the direction of energy transfer. And this is the easiest one to picture. So example, if you have a vibration in a stretched string of a musical instrument, for example, that is going to be a transverse wave. You pluck the string to the side, but the wave travels along the string. So that's 90 degrees between the direction of oscillation and the direction that the wave travels. And in fact, most of the examples that I'll go through today are going to be these transverse waves. A longitudinal wave, a little more difficult to picture. The medium vibrates parallel and anti-parallel to the direction that the wave goes. So it's like a backward and forward movement. And what this ends up doing is you get compressions and rarefactions. So this would be like compression is where the particles are getting a little closer together, and a rarefaction is where they're getting farther apart. So this would be called rarefaction. There's a compression here. You can see these are closer together. And then these are farther apart. This is a rarefaction. So if you keep track of like the pressure, this is why sometimes sound is called a pressure wave. When the particles are all close together, that's a high pressure region. When they're all spread apart, that's a lower pressure region. So the particles vibrate longitudinally, and then you've got these compressions and rarefactions moving along. So sound is an example of a longitudinal wave. Okay. And I have another animation of that on this page. This is showing, so sound is a longitudinal wave. What's showing here, this is like a speaker. And these are air particles, right? Air particles in a tube of air. So you can imagine if you have a tube and you have a speaker at one end of the tube, what you're doing here is you're sending sound waves through the tube of air. And so you have to kind of blur your eyes a little bit, but you can see that there's compression regions where the particles are sort of bunched up and they're moving steadily along. So I don't know if I can hover with this little dot. This is showing a compression moving along. That is moving, each compression is moving at the speed of sound from left to right. But the particles themselves, if you just look at this red particle or this red particle, all it's doing is just oscillating back and forth. And so this is a kind of an important property of waves in general, and is that the wave travels long distances, but the particles themselves just vibrate back and forth. And the way I try to remember this and think about it is I think of like a field of wheat. Sometimes if the wind is blowing across a big field of wheat, you will see these waves traveling along the field. You can see them, but obviously it's not the grass that's getting up and going along with those waves, right? The grass is attached to the ground. So all the grass is doing is oscillating back and forth, even though you can see these big waves traveling along. Well, it's the same with any kind of wave. The particles themselves don't move very far, but the waves themselves travel at these wave speeds and go a long way. Yeah, also baseball game, that's a good point. Robert just points out that they have the wave. And so if we were all in a big room together, like Convocation Hall right now, I would get you guys all to do the wave, where we would all stand up and go, whoa, and then sit back down. And then your neighbor stands up and sits back down, and we did the wave. So that's what I did last fall, but again. It's not really a COVID-friendly kind of thing to do. You guys want to do a poll? Okay. What is a transverse wave? Is it A, a wave in which the energy is transmitted in the opposite direction to the wave motion? B, a wave in which the energy is transmitted in the same direction as the wave motion? C, a wave in which the medium oscillates in a direction that is parallel to the direction of the wave energy travels? Or D, a wave in which the medium oscillates in a direction that is perpendicular to the direction the wave energy travels? One of those is what I just said. Can you spot it? When I see a hand there, Atang, did you want to unmute?
Yes, sir. I wanted to ask, what did you mean by disturbance when you're describing a wavefront?
Yeah, that's a really good question. So when I say disturbance, what I'm talking about is the source. So the source is doing something. It's usually accelerating or vibrating. And that's what bumps against all the other particles in the medium around it and creates these crests in the medium that then spread out. So I use the word sometimes disturbance to talk about the vibration of the particles themselves as they travel away. We just look quickly at 80% of you think, yeah, D. I don't know what all the other ones were, but I think that certainly D is describing a transverse wave. And in fact, I believe that this C is describing a longitudinal wave, right? And I don't know what these other ones describe. They didn't seem to make much sense to me, but they're definitely wrong. Okay, it's a good job. What is next? Yeah, so waves. So let's talk about waves in a string a little bit. And in fact, what I think I'll do right now is I'm going to exit this show and show you guys a cool little animation. And I'll post the link to this on the website after we break here. But it's called Wave on a String, and it's coming from PHET, which is the physics education thing. So what goes on here is if you shake one end of this, then it sends a wave along. Oh, and then it bounces off the end. Just goes back and forth. Can click on restart. This is going a little fast. I think we can put it in slow motion. Whatever I do on the left becomes a wave pulse, which then travels over to the right and then bounces off the end. It's sort of interesting and goes back and forth. Let's restart it. I think we can actually send a particular pulse, like a triangle, and see that going across. There's a nice triangular wave. So it goes along and it hits the end somehow. So right now, this is a simulation of what happens when you have a fixed end. Because the wave will go along, and actually, interestingly, it'll reflect in a negative way and come back. Interesting. Let's restart this. Now you can change the end of what happens to one of these, to a wave. You can have a fixed end. There's also a way to put a loose end, which is a ring attached to a frictionless vertical bar. And it still maintains the tension in the string, but if I send a pulse now, oops, it does something different at the end. Now you got a positive reflection. So that's kind of interesting. There's still a fixed end over here, so it'll be negative. If you get a negative wave on a loose end, then you'll get a negative reflection. So this is showing how waves can reflect when there's something. There's also something called no end. I love this one. So basically the end is very, very far away, somewhere off at infinity. And so if you send a pulse, what do you think will happen? It just goes bye-bye out the window. So that's sort of, it's just no end. Anyway, that's kind of fun. So then the other thing we can do is we can click on oscillate. So oscillate is when the source is a simple harmonic motion. So this is going up and down. Now they've driven this with a little circular drive or something so that this is one component of circular motion. So once again, this is going to be that x equals a times cosine of 2 pi over t times t. So when that happens, then every single particle is oscillating. So actually, let's look at this particle right here for a second. This particle is oscillating up and down with simple harmonic motion. It's because this is a transverse wave. And you can also see the crests traveling along from left to right. So there's all kinds of things going on here. There's each individual particle has an x velocity going, or sorry, a y velocity going up and down, and the y along parallel to the y-axis. And that's simple harmonic motion. And then in the x direction, you have this wave motion going from left to right. What else can we do? I think we can increase the frequency. Interesting. So when we increase the frequency, this goes up and down faster, and now it's still traveling at the same speed, so now these crests are closer together. What else can we do? We can increase the amplitude. And that doesn't change much, it just makes them bigger, but they're still the same spacing. We can lower the amplitude too if we want. They look a little different, but actually the spacing between the crests is still the same. The only way we can change that, the same frequency, is we could change the tension in the string. So this will change the wave speed in the string. I'll talk about that a little later. If there's lower tension and the waves slow down, oops, that's really low. And they end up getting closer together for the same frequency. How are people doing out there? Guys still there? Oh, a different end. That's a good question. Why don't we do that? We'll turn back up to high tension. I've got this in no end. So I've done this before. It can get a little crazy if you put it on fixed end. Let's do it. And actually, let's turn down the amplitude first before we do fixed end. We'll do it like that, and we'll hit restart, and then I'll fix the end. So what happens is the waves travel along, and then they reflect. And what happens when they reflect is that they interfere with each other, and then something weird starts to happen. You start to get what's called a standing wave. So that's why I didn't really go into this too much. And depending on the frequency of the standing wave, you can get a kind of a resonance. Anyway, it looks like that. So that's a little bit advanced. So Faison, thanks for that suggestion. That was a good idea. Okay. And yeah, and Osaze, this is superposition of two waves. There's a wave, there's the first wave coming from the source, and then there's all the reflected waves coming from that clamp, I guess, the C clamp with the right end. Oh, loose end, good. Marcia wants to see loose end, so let's do that. Because you can restart, click on loose end, see what happens. So remember, you get a reflected wave from a loose end as well. So it actually looks much the same. But now the right end is oscillating as well. And you don't get much. I think I have to adjust the frequency to see if I can get more of a... There'll be certain frequencies where you'll get a high amplitude, certain frequencies where you get a low amplitude. So I have to try to find this random frequency. And it differs depending if it's a fixed end or a loose end. Here we go. It's starting to really go. Although it looks a little weird though. And sometimes if you get just the right frequency, you can get the amplitude just skyrocketing, and you kind of break the animation. Try a little less. A little less. Let's try 2.3 hertz. Well, we'll see how. Anyway, it's fun to try play around with this thing. Okay, so that's it for that, and I'll post a link to that if you feel like playing around with it. It's also there's a app you can get on your phone, and fun stuff. So this is showing when you have a pulse on a heavy string attached to a lighter string, that boundary, if you have two strings tied together, is a little bit like a loose end. It goes up, and then your reflected wave is a positive reflected wave. And into the lighter string, you get a transmitted wave into that side, which is also positive. And it's larger. So that's another. You can also get a reflection from a heavier end. This is a little bit more like that C-clamp, the fixed end. You get a negative reflected pulse. And you get some, again, positive pulse, but it's a lower amplitude going into the second medium. Okay, so that's a little bit about reflection. I want to talk about snapshot versus history graphs. And this is coming, there's actually a homework 11 question on this. So a snapshot is kind of simple. It's just a graph that shows the waves displacement, I guess, the x position, or y position, I mean, when I say displacement, this is like y, as a function of position. Okay, so delta y is the displacement, up and down. I'll call this displacement. I think I also mentioned, a tongue pointed out that it's disturbance. I use various words for this, but I mean, how much it's going away from the particle's equilibrium position. And you plot that versus x. So it just is what the actual wave looks like as it goes by at a particular moment in time. And so for a one-dimensional wave, what will happen is that for different times, you will see the wave going along. And so if it's traveling from left to right, you'll see it first here, then here, then here. If you keep going, it'll eventually get farther and farther to the right. So the wave moves with constant speed, and this is what's pointed out in Atkina. The app, so yeah, if you want to see the app on my phone, where is it? What is it called? So Naomi is wondering if she can install the app. It's called PHET. So it's and it comes from University of Colorado. So PHET. The physics and education research department there. So that's to Naomi if you want to install it. And it's got lots and lots of physics animations, which could be useful even for physics 132. So V is showing you what the speed is delta x, how far in the x direction that the wave travels. Remember, the disturbance is in the y direction. We don't care about that. V is talking about how fast the shape of the wave moves. Oh, good. I actually didn't know that. You guys are doing this in practicals. I got to keep more on top of the practicals here. Thank you, Robert. Okay, yeah, so the next thing is a little tougher. It's called the history graph. The history graph shows the wave's displacement as a function of time at a single position. So, example is that, let's say we just thought about only x1 at the particle which sits at x1. Well, what happens to it? Well, first, I have to go back here. Yeah, there we go. First, it goes up the trailing edge. So at some time t, it starts, and then it gets to the top, and then it goes down the trailing edge there. So the way that looks, if you were to plot the position delta y of the particle at x1 over time, it would start here for a while, there'd be no wave. Then it would hit the first part of the wave, it would go up rapidly, and then it would go down after time. This is a little harder to picture, but if you imagine you had a stopwatch and just kept track of the time, this was what would happen to that particle. So do you want to do there's a question here that's actually from homework 11. Let's see if we can make it into a poll. The figure shows the displacement, so this figure on the right, displacement versus time graph of the left end, so the origin, x equals 0 of a 12-meter long rope. The wave velocity in the rope is plus 2 meters per second, means it's going to the right at 2 meters per second. Which graph below correctly shows a snapshot of the rope at t equals 5 seconds? And I will give you the choices on your device there. So I've given you the history graph. Which snapshot graph shows what the wave should look like at t equals 5? And then I'll discuss this and good. Maybe 5 seconds to click in. 10 seconds. Get some background noise there. Okay, let's see what people are saying. 43% of you who voted for that A. Let me show you what I'm kind of thinking. So this is all what's happening up here at the x equals 0, the left end of the rope. All of this, because that's a history graph. So at t equals 0, this wave starts, and then at t equals 3 seconds, so from here to here, this delta t is equal to 3 seconds, okay? And we know that delta x is equal to v times delta t, right? So, and we know that v is 2 meters per second, so delta x should be 6 meters. So you need one of these waves that's 6 meters long. This one's only 3 meters long, so that's not the right one. The rest of them, I think, are 6 meters long, so that's okay. This steep edge here is later. Steep edge is later in time on the clock, so it is the trailing edge. So the leading edge of the wave is the shallow one, and the trailing edge is the steep edge. So that that excludes this one, because the leading edge here is the steep one. So it's got to be either C or D. I would say that if the front of the wave, the back of the wave, the trailing part is at 3 seconds. At 3 seconds, it's at the origin. So at 5 seconds, so trailing edge is at x equals 0 at 3 seconds, according to the history graph. So 2 seconds later, it should be, the trailing edge should be at 4. This should be at 4 meters. So you need something, the trailing edge is at 4 meters. So that's wrong. So it's got to be this one. So I think it's got to be D, which 22% of you got. I followed my reasoning there. So one of the reasons I'm working from home is that my kids are going to be coming home for lunch soon. They're supposed to be home at about 12. I don't know if they'll burst into the door soon. So we do want to continue going here. When you get here, then I'm going to have to shut it off. And then, so my office hour is going to be at 1:30. I'll come back. So I'm going to be feeding them. So in these waves, what we had is different pulses, but you can set the pulse to be a sine wave, and that's what we did in the FET animation, right? So you can do you can say y is equal to some function of t and x is some cosine This is from the book. This is called a sinusoidal wave. If you put a minus sign here, it's traveling in the plus x direction. If you put a plus sign here, it turns out to be traveling in the negative x direction. So this is a kind of a lot of constants in this formula. The variables, so this thing right here is called lambda, in case you haven't seen that before. It's a Greek letter, which is the wavelength. I will say that y and x and t are variables, right? I think that t would be the independent variable, and then, no, actually t and x are the independent variables, and y is the dependent variable. So there's two independent variables, which is weird. The period capital T in seconds is the time for one complete vibration of a point in the medium. So actually, this is very similar to chapter 10. The frequency isn't listed here, but it would just be 1 over t. So a wave has a frequency. The amplitude is the maximum distance of a point in the medium from its equilibrium position as the wave passes. And what's not shown here is that there's a wave's speed. And the wave speed is going to turn out to be, so it's going to be lambda divided by capital T, or lambda times f. It's sort of a useful equation to have that. So how does this look? Well, we already saw a video of it. Let me try to show you what's going on. Here's a snapshot graph of a wave on a string. And what's shown here with the green arrows is the velocity of each particle. So remember, as the wave goes from left to right, the particles only travel up and down. So none of these arrows goes left or right, because that's not the direction the particles move. See if you guys can do this poll. See the point? This black dot? At this instant of time, which way is it moving? Actually, you know what I should put on here? Is, I forgot to do this, just in case. E is 0 velocity. If you want to do that. We do a quick thing here. I'm just going to quickly cut you guys off, and then I'm going to restart the polling. So right now, it's showing that 43% of the people who voted were voting A, and 41% were voting C. So that whoever did that one or the other, that's right. It is either A or C. It is moving for sure. And because it's a particle on transverse wave, it has to be going up or down. So the question is, now that we've kind of got that from you guys, is it A or is it C? And the way I try to think about this is that the wave is a pattern which is moving along from left to right. And the particles have to stay on the pattern. That's their job. And so when the pattern moves a little bit from left to right, imagine this particle, which is the black dot, which way would it have to move in order to stay on the pattern? Does it have to go up or down? There's some landscaping going on inside this window here. Okay, I'm going to give you 5 seconds. See what you guys think. Again, it looks pretty split here. This is a hard one. So the answer is A. But let's so 52% of you got that one, and this was a hard one, obviously. So what I think is that right now, this is now. And then what I could do, let's switch to like red for later. The pattern moves a little bit from left to right. This is later. So which way does the black dot have to move to stay on the pattern? If a little bit later, the pattern has moved from left to right. Well, it's going to have to go up. So the answer is A. Okay. All right. So that's a pretty tricky one. So just to kind of sum up, next slide here. Wave speed means the speed of the pattern. If you look at figure 11.8 on page 319, it shows 5 snapshots as a wave pattern moves from left to right in the plus x direction. So E here is showing that the pattern repeats at a distance t times v. And this distance is called the wavelength. Okay? So there's that equation I tried to write before. Lambda equals t times v. There's a few ways of rearranging it. But the main thing is you've got 3 constants there: wave speed, the period, and the wavelength. Those constants are related by this equation, and you can solve for any of them. I guess wave speed is going to be lambda over t. The period is going to be lambda over v, depending on which you want to solve for, right? And the wavelength is t times v. It's a useful equation. And then I think when we're talking about wave speed v, I think this is the last thing I'll do before my kids get here. When you have a transverse wave on a stretched string, then you have v is equal to f over mu. So this f is the tension. F is used for tension instead of t, since it's because we're running out of letters in the alphabet, since t is used for period. You're getting so far into physics that you're actually running out of letters in the English alphabet. Anyway, the tension is going to be in newtons, right? So it is a force. And then mu is a Greek letter. So again, since we don't have enough letters in the English alphabet, might as well go to Greek, right? This is called mu. It's the favorite letter of Greek cows, I guess. It is the linear density of the string. So the mass of the string divided by its length. So its units are kilograms per meter. So let me do one quick question for you. I'll do this example on Friday, actually, on Crazy Friday. But let's do this one as a poll. For a wave pulse on a string to travel twice as fast, how should you adjust the string tension? Should you increase it by a factor of 4, increase it by a factor of 2, decrease it to a half of its initial value, decrease it to a fourth of its initial value, or it's not possible? The pulse speed is always the same no matter what the tension is. Let's do a poll. Okay, should see the poll now. And I told those kids to come up and knock when they get home. Maybe they'll come on the call. So the equation here, I'll write it again. V is equal to the square root of F over mu. So mu is the same because you're using the same string. F is tension in newtons. So it's sort of weird. It turns out that somehow the square root of newtons divided by meters per kilogram turns out to be meters per second. You can check that. Okay. So right, you have to, if F goes up by a factor of 4, then the V will go up by a factor of the square root of 4. Okay, and you'll get pulses that are going twice as fast. So that was really good. So again, I'm gonna have to run. I will be back in the TA Help Center at 1:30 today. So office hour. I made an announcement today. is at 1:30 p.m. today only. I'm going to log off. I would like you to continue reading chapter 11. I'm going to do some examples on this wave and a string stuff when we come back on Friday. There will also be a team-up quiz on chapter 11 stuff that we've been starting on here during Friday's class. It's going to be called Team-Up Quiz Module 6, Chapter 11. You'll find out in Module 6, which is just Chapter 11. There's no midterm in Module 6. It'll be available all weekend if you're on the YouTube or something like that. But I hope to see you in class on Friday, and we'll have Crazy Friday. So take care, everybody. Thanks very much. I'm going to go tend to my kids. And if you want to see me in the office hour, otherwise I'll see you on Friday. Let's do stop share. And